Find out all types of printed circuit boards, PCBs, and their applications. Printed circuit boards, PCBs, come in various types, each designed for specific applications and requirements. Here are some common types of PCBs. Single-sided PCBs are one of the simplest and most basic types of printed circuit boards, PCBs. They are characterized by having copper traces and components mounted on only one side of the PCB substrate. Here are some key characteristics and considerations for single-sided PCBs. Construction: single-sided PCBs consist of a single layer of substrate material, typically made of fiberglass reinforced epoxy, FR4, or phenolic paper. On one side of the substrate, a thin layer of copper is bonded. Component mounting: all electronic components, such as resistors, capacitors, diodes, and integrated circuits, are soldered onto the side with the copper traces. The other side remains unpopulated. Copper traces: copper traces are used to establish electrical connections between the components. These traces are created by selectively etching away the excess copper from the board, leaving behind the desired circuit pattern. Through-hole components: through-hole components are commonly used on single-sided PCBs. These components have wire leads that pass through holes in the PCB and are soldered on the opposite side. Soldering: soldering is done on the copper side, where components are mounted. It's crucial to ensure proper soldering to maintain electrical connectivity and reliability. Cost-effective: single-sided PCBs are cost-effective and relatively simple to manufacture due to their single-layer design, making them suitable for applications with budget constraints. Applications: single-sided PCBs are used in various low-complexity and low-cost electronic devices, including toys, calculators, simple power supplies, and some consumer electronics with basic functionality. Limitations: they have limited routing options because all traces must be on one side, which can lead to larger board sizes and less complex circuit designs. This makes them unsuitable for complex, high-density, or high-frequency applications. Prototyping: single-sided PCBs are sometimes used for prototyping and educational purposes due to their simplicity and cost-effectiveness. Assembly and repair: repairing and modifying single-sided PCBs is relatively straightforward since components are accessible from one side. However, space constraints can limit modifications. In summary, single-sided PCBs are a basic type of PCB suitable for simple electronic applications where cost and complexity are critical factors. They are easy to manufacture and assemble but have limitations in terms of circuit complexity and component density compared to more advanced PCB types like double-sided or multi-layer PCBs. Double-sided PCBs, also known as two-layer PCBs, are a more versatile and commonly used type of printed circuit board compared to single-sided PCBs. They offer greater design flexibility and are suitable for a wide range of electronic applications. Here are some key characteristics and considerations for double-sided PCBs. Construction: double-sided PCBs consist of a substrate material, typically made of fiberglass reinforced epoxy, FR4, with copper traces on both sides of the board. The copper layers are bonded to each side of the substrate. Component mounting: electronic components such as resistors, capacitors, integrated circuits, and more, can be mounted on both sides of the PCB. This allows for a higher component density and more complex circuit designs. Copper traces: copper traces on both sides of the board are used to establish electrical connections between components. Traces are created by selectively etching away the excess copper to form the desired circuit patterns. Through-hole and surface mount components: double-sided PCBs can accommodate both through-hole and surface mount components. This versatility allows for a broader range of component choices and design options. Via holes: to establish connections between the top and bottom copper layers, via holes are used. These are small holes drilled through the substrate and plated with copper to create electrical connections between the layers. Soldering: components can be soldered onto both sides of the PCB. Soldering requires careful attention to avoid solder bridges between adjacent traces, especially on densely populated boards. Cost: double-sided PCBs are more complex and require additional processing steps compared to single-sided PCBs, making them moderately more expensive but still cost-effective for most applications. Applications: double-sided PCBs are widely used in various electronic devices, including consumer electronics, industrial control systems, automotive applications, medical devices, and more. They strike a balance between complexity and cost. Routing flexibility: the use of two layers allows for more intricate routing and greater design flexibility compared to single-sided PCBs. This makes them suitable for designs with moderate complexity. Signal isolation: double-sided PCBs can isolate signals and components on separate layers, reducing interference and crosstalk between adjacent traces. Prototyping and production: double-sided PCBs are commonly used for both prototyping and mass production of electronic devices. They strike a balance between cost and complexity, making them suitable for a wide range of applications. In summary, double-sided PCBs are a versatile and widely used option for electronic circuit design and production. They offer greater flexibility and complexity compared to single-sided PCBs while remaining cost-effective for most applications. Their ability to accommodate a mix of through-hole and surface-mount components makes them suitable for a broad range of electronic devices and systems. Multi-layer PCBs, also known as multi-layer printed circuit boards, are a more advanced and complex type of PCB that offers significant advantages in terms of circuit density, performance, and functionality. They are widely used in modern electronics, particularly in high-performance and compact devices. Here are some key characteristics and considerations for multi-layer PCBs. Construction: multi-layer PCBs are constructed by sandwiching multiple layers of dielectric material, typically fiberglass reinforced epoxy or FR4, between layers of copper foil. Each layer consists of a copper plane for routing signals and power planes for distributing power and managing heat. Number of layers: multi-layer PCBs can have two or more layers, with the number of layers determined by the complexity of the circuit and the specific requirements of the application. Common options include 4-layer, 6-layer, 8-layer, and even higher-layer PCBs. Component mounting: electronic components can be mounted on both sides of the PCB, just like double-sided PCBs. However, the additional layers provide more space for components, enabling higher component density and more complex designs. Copper traces: multi-layer PCBs have copper traces on multiple layers, allowing for intricate routing of signals. The layers are interconnected through plated through-hole vias or surface-mounted blind/buried vias. Via types: plated through-hole vias, PTH, extend through all layers of the PCB, connecting traces on different layers. Blind vias connect an outer layer to one or more inner layers but do not extend through the entire PCB thickness. Buried vias connect inner layers without touching the outer layers. Signal integrity: multi-layer PCBs provide better signal integrity and reduce electromagnetic interference (EMI) and crosstalk due to the isolation of signal traces within inner layers. This is especially important for high-speed and high-frequency applications. Power distribution: multi-layer PCBs use dedicated power planes for efficient power distribution and heat dissipation. This helps manage power and thermal requirements effectively, critical in power electronics and high-power applications. Complexity and performance: multi-layer PCBs can handle complex digital and analog circuits, making them suitable for advanced electronic devices, including smartphones, computers, networking equipment, and advanced medical devices. Cost: multi-layer PCBs are more expensive to manufacture than single-sided or double-sided PCBs due to the increased layer count and additional manufacturing steps. However, the benefits often outweigh the higher cost for applications demanding advanced functionality. Prototyping and mass production: multi-layer PCBs are used in both prototyping and mass production stages of electronic device development. They offer the necessary scalability and performance for high-volume production. In summary, multi-layer PCBs are the go-to choice for modern electronics that require high component density, complex circuitry, signal integrity, and reliable power distribution. Their ability to accommodate advanced designs and manage heat and electromagnetic interference makes them essential for a wide range of applications in today's technology-driven world. Rigid PCBs, or rigid printed circuit boards, are a type of PCB known for their inflexible and solid construction. These boards are commonly used in a wide range of electronic devices and applications due to their stability and durability. Here are some key characteristics and considerations for rigid PCBs. Construction: rigid PCBs are typically constructed with a solid and rigid substrate material, commonly made of fiberglass reinforced epoxy, FR4, or phenolic paper. The substrate provides mechanical support and electrical insulation. Single or multiple layers: rigid PCBs can have one or multiple layers, depending on the complexity of the circuit. Single-layer rigid PCBs are simpler and cost-effective, while multi-layer rigid PCBs are used in more complex applications. Component mounting: electronic components are mounted on the rigid PCB using soldering techniques. Both through-hole and surface mount components can be used, allowing for flexibility in component selection and placement. Copper traces: copper traces on the PCB's surface are used to create electrical connections between components. These traces are typically etched onto the surface of the board and provide the conductive pathways for electrical signals. Strength and durability: rigid PCBs are known for their mechanical strength and durability. They can withstand physical stress, making them suitable for applications where the board may be subjected to mechanical loads or vibrations. Applications: rigid PCBs are used in a wide range of electronic devices and equipment, including consumer electronics, e.g., smartphones, televisions, industrial controls, automotive electronics, medical devices, and more. Complexity: rigid PCBs can accommodate circuits of varying complexity. While single-layer rigid PCBs are used for simpler applications, multi-layer rigid PCBs can handle highly complex circuit designs. Size and form factor: rigid PCBs come in various sizes and shapes, making them adaptable to different design requirements. They can be rectangular, square, or customized to fit specific enclosures or spaces within a device. Cost: the cost of rigid PCBs can vary depending on factors such as board size, layer count, and complexity. Single-layer boards are generally more cost-effective than multi-layer boards. Prototyping and mass production: rigid PCBs are used in both prototyping and mass production stages of electronic device development. They are suitable for a wide range of production volumes, from small runs to large-scale manufacturing. Heat dissipation: while rigid PCBs can dissipate some heat, they are not as efficient in managing heat as specialized boards like metal core PCBs or flexible PCBs with built-in heat sinks. Additional heat management solutions may be required for high-power applications. In summary, rigid PCBs are a fundamental and widely used type of printed circuit board in the electronics industry. Their mechanical strength, durability, and adaptability to various applications make them a go-to choice for many electronic devices, from consumer products to industrial and medical equipment. Flexible PCBs, also known as flex PCBs or flexible printed circuit boards, are a specialized type of PCB designed to be highly flexible and bendable. They offer unique advantages in applications where traditional rigid PCBs would be unsuitable due to their flexibility and durability. Here are some key characteristics and considerations for flexible PCBs. Construction: flexible PCBs are made from flexible substrate materials such as polyimide, PI, or polyester, PET. These materials provide excellent flexibility while maintaining electrical insulation properties. Flexibility: as the name suggests, flexible PCBs can bend, twist, and conform to non-planar surfaces. This flexibility is particularly useful in applications where space is limited or where the PCB needs to follow a specific form or contour. Single or multiple layers: flexible PCBs can be single-sided or double-sided, and they can also have multiple layers like rigid PCBs. A multi-layer flex PCBs are used in applications requiring complex circuitry. Component mounting: electronic components can be mounted on both sides of flexible PCBs, similar to rigid PCBs. Through-hole and surface mount components are commonly used, depending on the design requirements. Copper traces are etched onto the flexible substrate to create electrical connections. These traces are typically thin and lightweight, making them suitable for flexible applications. Flex life: flexible PCBs are designed for repeated flexing, which is measured in terms of flex life. The flex life of a flex PCB depends on factors like the material used, design, and the degree of bending required. Applications: flexible PCBs are used in various applications, including wearable devices, medical equipment, automotive systems, aerospace applications, and any devices or systems where space constraints or flexibility are critical. Weight and size: flexible PCBs are lightweight and can be made in smaller form factors than their rigid counterparts. This makes them ideal for miniaturized and lightweight electronic devices. Cost: the manufacturing of flexible PCBs can be more complex and costly than rigid PCBs due to the specialized materials and processes involved. However, they offer unique advantages that justify the cost in specific applications. Prototyping and mass production: flexible PCBs are used for both prototyping and mass production, particularly in industries where flexibility and durability are essential. Heat management: flexible PCBs have limited heat dissipation capabilities compared to rigid PCBs. If an application generates significant heat, additional thermal management solutions may be required. Connector and termination options: connectors designed for flexible PCBs, such as ZIF, zero insertion force, connectors, are used to interface with rigid boards or other components. Termination methods for flexible PCBs can vary depending on the application. In summary, flexible PCBs offer unique advantages in applications where traditional rigid PCBs cannot meet the requirements due to their flexibility, lightweight nature, and ability to conform to complex shapes. They are particularly well suited for applications demanding durability, miniaturization, and adaptability to non-planar surfaces. Rigid flex PCBs, short for rigid flexible printed circuit boards, are a specialized type of PCB that combines elements of both rigid and flexible PCBs. They are designed to provide the benefits of both rigid and flexible boards, making them ideal for applications that require a combination of structural stability and flexibility. Here are some key characteristics and considerations for rigid flex PCBs. Construction: rigid flex PCBs consist of rigid sections and flexible sections, which are joined together to form a single PCB. The rigid sections are typically made from materials like fiberglass reinforced epoxy, FR4, while the flexible sections use materials such as polyimide, PI, or polyester, PET. Flexibility: the flexible sections of a rigid flex PCB allow it to bend, fold, and conform to non-planar shapes or enclosures. This flexibility is useful for applications where the PCB needs to fit into tight spaces or follow complex contours. Component mounting: electronic components can be mounted on both the rigid and flexible sections of the PCB. Through-hole and surface mount components are commonly used, providing design flexibility. Copper traces are used on both the rigid and flexible sections to create electrical connections. The traces are carefully designed to accommodate the bending and flexing of the flexible sections without compromising electrical integrity. Via types: rigid flex PCBs use various via types, including through-hole vias that pass through both rigid and flexible sections and blind/buried vias that connect layers within the rigid sections. These vias allow for electrical connections between different sections and layers of the PCB. Applications: rigid flex PCBs are used in a wide range of applications where a combination of rigidity and flexibility is required. Common applications include aerospace and aviation systems, medical devices, military equipment, automotive electronics, and any device with space or design constraints. Complexity: rigid flex PCBs can accommodate complex circuit designs, making them suitable for high-density and high-performance applications. They offer the advantages of both rigid and flexible PCBs, allowing designers to optimize their layouts. Size and weight: rigid flex PCBs can reduce the overall size and weight of electronic devices compared to using separate rigid and flexible PCBs. This is particularly valuable in miniaturized or lightweight applications. Cost: rigid flex PCBs can be more expensive to manufacture than rigid or flexible PCBs due to their complexity and specialized materials. However, they often provide cost savings in terms of reduced assembly and integration costs. Connector integration: rigid flex PCBs can incorporate connectors and terminations directly into the board, reducing the need for additional interconnect components and improving reliability. Heat management: like flexible PCBs, rigid flex PCBs have limited heat dissipation capabilities compared to pure rigid PCBs. Adequate heat management solutions should be considered for applications with high heat generation. In summary, rigid flex PCBs offer a versatile solution for applications that demand both structural stability and flexibility. Their ability to accommodate complex designs, reduce size and weight, and simplify assembly make them a valuable choice in industries where space constraints and reliability are critical. High-frequency PCBs are specialized printed circuit boards designed to operate at radio frequencies, RF, or microwave frequencies. These PCBs are engineered to ensure optimal signal integrity, minimal signal loss, and efficient energy transfer at high frequencies. Here are some key characteristics and considerations for high-frequency PCBs. Substrate material: the choice of substrate material is critical in high-frequency PCBs. Common materials include specialized laminates like PTFE, polytetrafluoroethylene, RO4000 series, or other low-loss materials with low dielectric constant, dK, and low dissipation factor, dF. These materials minimize signal loss and reduce interference. Copper foil: high-frequency PCBs often use thinner copper foil than standard PCBs to minimize conductor losses. Foil with high purity and low surface roughness is preferred to ensure efficient signal transmission. Tightly controlled dielectric constants: maintaining a consistent and tightly controlled dielectric constant, dK, across the PCB is crucial for predictable impedance matching. Variations in dK can lead to signal distortion and reflection. Precise traces in ground planes: high-frequency PCBs require precise control over trace widths, spacing, and impedance. Additionally, ground planes are carefully designed to provide a low impedance return path for RF signals. RF connectors and transmission lines: RF connectors and transmission lines, such as microstrip or stripline, are used to ensure controlled impedance and minimize signal losses when connecting external RF components. Via design: specialized via structures, like plated through holes, PTHs, with carefully controlled diameters, are used to maintain signal integrity when transitioning between different PCB layers. EMI shielding: high-frequency PCBs may require additional electromagnetic interference (EMI) shielding to prevent unwanted radiation and to maintain signal purity. Component placement: component placement on high-frequency PCBs is critical to minimize signal path lengths and reduce parasitic capacitance and inductance. Testing and validation: high-frequency PCBs often undergo extensive testing and validation to ensure that they meet specific RF performance requirements. This may include testing for insertion loss, return loss, and impedance matching. Applications: high-frequency PCBs are used in a wide range of applications, including telecommunications equipment, radar systems, satellite communication, microwave devices, wireless networking equipment, Wi-Fi, cellular, and 5G, and high-speed data transmission systems. Specialized design software: engineers designing high-frequency PCBs often use specialized simulation and design software to model and optimize the RF performance of the board before fabrication. Cost: high-frequency PCBs can be more expensive to manufacture than standard PCBs due to the use of specialized materials and precise manufacturing processes. However, the cost is justified in applications where RF performance is critical. In summary, high-frequency PCBs are essential in applications where precise signal integrity at RF and microwave frequencies is crucial. Their design considerations, material choices, and fabrication processes are tailored to ensure minimal signal loss, impedance matching, and reliable performance in high-frequency environments. High-density interconnect (HDI) PCBs are specialized printed circuit boards designed to maximize component density and reduce the overall size of electronic devices. HDI PCBs use advanced manufacturing techniques and technologies to achieve higher wiring densities, finer trace widths and spacing, and increased layer counts compared to traditional PCBs. Here are some key characteristics and considerations for HDI PCBs. Advanced technology. HDI PCBs leverage cutting-edge manufacturing technologies, including laser drilling, sequential lamination, and microvia technology, to achieve high component density and smaller feature sizes. Microvias are tiny, laser-drilled holes used to connect different layers of the PCB. They allow for more routing channels and greater routing flexibility, contributing to increased component density. Blind and buried vias. HDI PCBs often use blind and buried vias, which connect inner layers without extending through the entire board. These vias reduce layer-to-layer signal interference and enhance overall design flexibility. Fine trace widths and spacing. HDI PCBs feature very fine traces and spacing, allowing for more intricate routing of signals. This is particularly useful in high-performance and miniaturized electronic devices. Multiple layer stacking. HDI PCBs can have multiple layers stacked closely together, increasing the number of routing channels and enabling complex, high-density designs. Smaller form factors. HDI PCBs are ideal for reducing the size and weight of electronic devices. They enable designers to create smaller and more compact products. Component placement. Components can be densely packed on both sides of the PCB, maximizing the use of available space. Surface mount technology. SMT HDI PCBs are well suited for surface mount components, which are smaller and can be placed more closely together than through-hole components. Applications. HDI PCBs are used in a wide range of applications, including smartphones, tablets, laptop computers, IoT devices, medical devices, and any electronic device where miniaturization and high performance are critical. Cost. HDI PCBs can be more expensive to manufacture than traditional PCBs due to the complexity of the manufacturing process and the use of advanced materials and techniques. However, the benefits often justify the cost, especially in applications where space and performance constraints are essential. Design software. Engineers designing HDI PCBs typically use specialized design software to optimize the layout, routing, and stack-up of the board to achieve the desired high-density configuration. Testing and validation. HDI PCBs may require thorough testing and validation to ensure signal integrity, impedance matching, and overall reliability, given their high component density and intricate design. In summary, HDI PCBs are a crucial solution for electronic devices requiring high component density, miniaturization, and enhanced performance. Their use of advanced manufacturing techniques and materials allows designers to create smaller, more compact, and highly functional electronic products across various industries. Metal core PCBs. MCPCBs, also known as metal core printed circuit boards or thermal PCBs, are a type of printed circuit board with a metal core layer that offers superior heat dissipation properties. These boards are designed to effectively dissipate heat generated by high-power electronic components and are commonly used in applications where thermal management is critical. Here are some key characteristics and considerations for metal core PCBs. Metal core. The core layer of MCPCBs is made of a thermally conductive material, usually aluminum or copper. This metal core acts as a heat sink, efficiently dissipating heat away from heat-generating components. Dielectric layer. Above the metal core, MCPCBs have a dielectric layer, typically made of thermally insulating materials like fiberglass reinforced epoxy, FR4. The dielectric layer electrically isolates the circuit traces from the metal core. Copper traces. On top of the dielectric layer, copper traces are etched or deposited to create the circuit connections. These traces carry electrical signals and power between components while being thermally insulated from the metal core. Thermal performance. MCPCBs excel at dissipating heat, making them suitable for high-power and high-temperature applications. The metal core provides a low thermal resistance path for heat to flow away from components, helping maintain their operational reliability. Applications. MCPCBs are commonly used in applications requiring effective thermal management, such as LED lighting, power electronics, e.g., power supplies and motor drives, automotive lighting, high-power amplifiers, and industrial controls. Light-emitting diodes, LEDs. MCPCBs are widely used in LED applications, as they help maintain optimal operating temperatures for LEDs, improving their efficiency and lifespan. Customizable design. MCPCBs can be customized to accommodate various component placements and configurations, making them versatile for different product designs. Soldering and assembly. Components on MCPCBs are typically soldered using standard surface mount technology, SMT, or through-hole technology, THT, assembly processes. Cost. MCPCBs are often more expensive to manufacture than standard FR4 PCBs due to the cost of the metal core material and additional manufacturing processes. However, the cost is justified in applications where heat management is crucial. Prototyping and mass production. MCPCBs can be used in both prototype development and large-scale production, depending on the specific application and volume requirements. Design considerations. Designers need to consider factors such as thermal pad placement, copper thickness, and the choice of metal core material to optimize the board's thermal performance. Testing and validation. MCPCBs may undergo thermal testing to ensure they meet thermal performance requirements and can effectively dissipate heat generated during operation. In summary, metal core PCBs are essential for applications where efficient heat dissipation is critical. Their ability to handle high temperatures and manage thermal loads makes them suitable for various industries, especially those involving high-power electronics and LED lighting. Ceramic printed circuit boards, ceramic PCBs, are specialized printed circuit boards that use ceramic materials as the substrate instead of traditional materials like fiberglass reinforced epoxy, FR4. Ceramic PCBs offer unique advantages, particularly in applications where thermal performance, high-frequency operation, and reliability are critical. Here are some key characteristics and considerations for ceramic PCBs. Ceramic substrate. The core material of ceramic PCBs is typically made of ceramics like aluminum oxide, Al2O3, or aluminum nitride, Ln. These ceramics provide excellent thermal conductivity and electrical insulation properties. Thermal performance. Ceramic PCBs are known for their exceptional thermal performance. They can efficiently dissipate heat generated by high-power electronic components, making them suitable for high-temperature environments. Dielectric constant. Ceramic materials used in PCBs often have a stable and low dielectric constant, dK, which is important for high-frequency applications. This ensures minimal signal loss and excellent signal integrity. Low dissipation factor. Ceramics typically have a low dissipation factor, DF, which means they have low energy loss when transmitting high-frequency signals. This property is crucial for minimizing signal attenuation. High-frequency operation. Ceramic PCBs are well suited for high-frequency and microwave applications, such as RF amplifiers, radar systems, and wireless communication equipment. Component mounting. Electronic components can be mounted on ceramic PCBs using standard surface mount technology, SMT, or through-hole technology, THT, assembly processes. Thermal management. The high thermal conductivity of ceramics allows for efficient heat spreading and dissipation, reducing the risk of overheating electronic components. Applications. Ceramic PCBs are commonly used in demanding applications like RF/microwave circuits, power amplifiers, automotive electronics, aerospace systems, and any application requiring high reliability and high temperature operation. Cost. Ceramic PCBs are typically more expensive to manufacture than standard FR4 PCBs due to the cost of ceramic materials and specialized manufacturing processes. However, their performance benefits often justify the higher cost. Prototyping and mass production. Ceramic PCBs can be used in both prototype development and mass production, depending on the specific application and volume requirements. Design considerations. Designers must consider factors such as the choice of ceramic material, thickness, and the specific requirements of the application when designing ceramic PCBs. Testing and validation. Due to their use in high-frequency and high-reliability applications, ceramic PCBs often undergo rigorous testing and validation processes to ensure they meet the performance and reliability requirements. In summary, ceramic PCBs are a specialized type of PCB that excels in high temperature and high frequency applications. Their excellent thermal properties, low signal loss, and reliability make them essential in industries where performance and durability are paramount. RF, radio frequency, and microwave PCBs are specialized printed circuit boards designed to operate at high frequencies, typically ranging from hundreds of megahertz, to many gigahertz. These PCBs are optimized for applications where signal integrity, impedance matching, and minimal signal loss are critical. Here are some key characteristics and considerations for RF and microwave PCBs. Substrate material. The choice of substrate material is critical for RF and microwave PCBs. High-frequency laminates with low dielectric constant, dK, and low loss tangent, dF, such as Rogers materials, are commonly used. These materials minimize signal loss and ensure predictable impedance characteristics. Trace geometry. RF and microwave PCBs use specialized trace geometries, such as microstrip or stripline, to maintain controlled impedance and minimize signal reflections. The choice of trace width, spacing, and thickness is carefully considered. Copper plating. High-quality, smooth copper plating with minimal surface roughness is essential to reduce signal loss at high frequencies. Ground planes. RF and microwave PCBs feature dedicated ground planes to provide a low impedance return path for signals. These planes help reduce electromagnetic interference, EMI, and crosstalk. Connector integration. RF connectors, coaxial connectors, and transmission lines are used to ensure controlled impedance and minimal signal loss when interfacing with external RF components and devices. Via design, special attention is given to via structures, including plated through-hole vias and blind vias, to maintain signal integrity and impedance matching between different layers. Component placement. Component placement is carefully optimized to minimize trace lengths and reduce parasitic capacitance and inductance. EMI shielding. RF and microwave PCBs may incorporate EMI shielding features to prevent unwanted radiation and maintain signal purity. Applications. RF and microwave PCBs are used in applications such as wireless communication systems, e.g., cellular base stations, radar systems, satellite communication, microwave devices, and test and measurement equipment. Testing and validation. RF and microwave PCBs undergo extensive testing, including Vector Network Analyzer (VNA) testing, to validate their RF performance and ensure they meet stringent specifications. Cost. Due to the specialized materials and manufacturing processes involved, RF and microwave PCBs can be more expensive to produce than standard FR4 PCBs. However, they are essential in applications where high-frequency performance is critical. Prototyping and mass production. RF and microwave PCBs are used in both prototype development and mass production, depending on the specific application and volume requirements. Design software. Engineers designing RF and microwave PCBs often use specialized simulation and design software to model and optimize the RF performance of the board before fabrication. In summary, RF and microwave PCBs are essential for applications where high-frequency signal integrity, impedance matching, and minimal signal loss are paramount. Their specialized design and materials make them ideal for industries such as telecommunications, aerospace, defense, and wireless technology. Insulated metal substrate, IMS, PCBs, also known as metal core PCBs, MCPCBs, are a specialized type of printed circuit board designed for applications that require efficient thermal management and enhanced heat dissipation. IMS PCBs consist of a metal core, typically aluminum or copper, with a layer of thermally insulating dielectric material that separates the metal core from the circuit traces. Here are some key characteristics and considerations for IMS PCBs. Metal core. The core of an IMS PCB is made of a thermally conductive metal, most commonly aluminum or copper. This metal core serves as an effective heat sink, allowing for the efficient dissipation of heat generated by electronic components. Dielectric layer. Above the metal core, there is a dielectric layer, which is typically composed of materials like polyimide, PI, or epoxy resin with ceramic fillers. This dielectric layer provides electrical insulation between the metal core and the circuit traces. Circuit traces. Circuit traces are typically made of copper and are patterned on the dielectric layer. These traces are responsible for carrying electrical signals and power between components while being thermally isolated from the metal core. Thermal performance. IMS PCBs are highly effective at dissipating heat, making them ideal for high power and high temperature applications. The metal core efficiently conducts heat away from heat-generating components, helping to maintain their operational reliability. Thermal management. IMS PCBs are particularly well suited for applications that require effective thermal management, such as LED lighting, power electronics, e.g., power supplies and motor drives, automotive electronics, and industrial controls. LED applications. IMS PCBs are widely used in LED applications to maintain optimal operating temperatures for LEDs, ensuring improved efficiency and extended lifespan. Component mounting. Electronic components can be mounted on IMS PCBs using standard surface mount technology, SMT, or through-hole technology, THT, assembly processes. Applications. IMS PCBs find applications in a wide range of industries, including LED lighting, automotive, telecommunications, renewable energy systems, and any application where effective thermal management is critical. Cost. IMS PCBs can be more expensive to manufacture than standard FR4 PCBs due to the cost of the metal core and specialized manufacturing processes. However, the cost is often justified by the improved thermal performance and reliability. Prototyping and mass production. IMS PCBs can be used in both prototype development and mass production, depending on the specific application and volume requirements. Design considerations. Designers must consider factors such as the choice of metal core material, aluminum or copper, the thickness of the dielectric layer, and the specific requirements of the application when designing IMS PCBs. Testing and validation. Due to their use in high power and high temperature environments, IMS PCBs often undergo testing to ensure they meet thermal performance requirements and can effectively dissipate heat during operation. In summary, insulated metal substrate, IMS, PCBs are essential for applications where efficient thermal management and heat dissipation are critical. Their ability to handle high temperatures and manage thermal loads effectively makes them suitable for various industries, especially those involving high-power electronics and LED lighting. Backplane PCBs, often referred to simply as backplanes, are specialized printed circuit boards designed for interconnecting various electronic components and modules within a complex electronic system. Backplanes serve as a central backbone or interconnect infrastructure, allowing for the seamless exchange of data, signals, and power between multiple boards, modules, or cards in a larger system. Here are some key characteristics and considerations for backplane PCBs. Interconnect hub. Backplanes function as the central interconnect hub in electronic systems, serving as a common point of connection for multiple boards or modules. They enable communication between these boards and often facilitate data, control, and power distribution. High-density connectors. Backplanes feature high-density connectors, such as edge connectors or card edge connectors, to interface with plug-in cards or modules. These connectors provide multiple electrical contacts for reliable connections. Bus structures. Backplanes often incorporate bus structures, such as parallel or serial buses, to allow for data transfer between interconnected boards. These buses can include PCI, PCI VME, or custom design interfaces, depending on the application. Customizable design. Backplane designs are highly customizable to accommodate the specific requirements of the system. This includes the number and type of connectors, board size, and the routing of traces to ensure proper signal integrity. Multiple layers. Backplane PCBs are typically multi-layer boards with multiple signal layers, power distribution planes, and ground planes. This helps manage signal integrity, reduce electromagnetic interference, EMI, and ensure proper power distribution. Signal integrity. Maintaining signal integrity is crucial in backplane design. Techniques such as controlled impedance routing and signal equalization may be employed to minimize signal degradation over long traces. Hot swap capability. Some backplane designs incorporate features that allow for hot swapping or the insertion and removal of cards or modules without powering down the system. This is especially important in mission-critical applications. Redundancy and fault tolerance. In applications where system reliability is paramount, backplanes may include redundant paths or components to ensure continued operation in case of a failure. Cooling solutions. Depending on the power and thermal requirements of the system, backplanes may be designed to accommodate cooling solutions such as fans, heat sinks, or airflow channels. Applications. Backplanes are used in a wide range of applications, including telecommunications equipment, data centers, industrial automation, military and aerospace systems, and rack-mounted servers. Testing and validation. Backplanes undergo extensive testing to ensure proper functionality, signal integrity, and reliability. This includes electrical testing, mechanical testing, and validation of power distribution and cooling. Cost. The cost of backplane PCBs can vary widely depending on the complexity of the design, the number of connectors, and other customization factors. In summary, backplane PCBs play a critical role in complex electronic systems by providing the necessary infrastructure for interconnecting multiple boards or modules. Their design considerations focus on ensuring reliable and high-speed data exchange, signal integrity, and system flexibility, making them essential components in a wide range of applications.